This research paper introduces ClickDiff, a controllable conditional generation model that leverages a fine-grained semantic contact map, SCM, for grasp generation. The proposed method addresses the limitations of traditional approaches, which focus on visibility and diversity under scene constraints, often overlooking fine-grained hand-object interactions such as contacts. The authors propose a controllable grasp generation task, enabling the precise control of grasp synthesis through user-specified or algorithmically predicted SCM. The key insight is that hand joint movements are largely driven by finger geometry, and explicitly modeling finger-object contact during training and inference can serve as a powerful proxy guide. The authors introduce SCM, a novel contact representation method that obtains representations of points on the object that are touched and the fingers touching those points. SCM enables customization through clicking to achieve user-controlled interactive generation. The proposed dual generation framework consists of two modules: the Semantic Conditional Module, which generates contact maps using SCM as conditions, and the Contact Conditional Module, which synthesizes hand grasps based on generated contact maps and object point cloud information as conditions. The tactile guided constraint is introduced to extract pairs in the SCM that represent touching and integrate contact information into the Contact Conditional Module. The authors evaluate the evaluation criteria applicable to controllable grasp generation, demonstrating the validity and robustness of ClickDiff on the GRAB and Arctic datasets, even with previously unseen objects. The proposed method achieves more natural and precise generation results compared to conventional methods that rely solely on contact maps. In summary, the contributions of this paper include proposing the controllable grasp generation task, introducing SCM, and developing a dual generation framework that enables precise generation through user-specified or algorithmically predicted SCM. The authors demonstrate the efficacy of ClickDiff in generating realistic and controllable grasps, addressing the contact ambiguity issue in direct contact map generation. This research endeavors to address the challenge of controllable grasp generation, focusing on fine-grained contact information between fingers and objects. The proposed method, ClickDiff, utilizes a conditional diffusion model framework to improve the fidelity of generation through user-specified contacts. The authors first discuss related work in controllable human-object interaction and grasp generation. Recent methods have shifted focus towards predicting static human poses that are congruent with environmental constraints, particularly in scenarios involving affordances and hand-object interactions. However, a gap remains in methods that specifically address fine-grained interactions, particularly the nuanced contacts involved in hand-object interactions. To address this, the authors propose a controllable contact representation called the Semantic Contact Map, SCM, which simultaneously represents the fine-grained contacts between fingers and objects. SCM is a 2D matrix that indicates the points on the object that are being touched and the finger parts touching these points. Each point may be touched by more than one finger. The authors then introduce a dual generation framework, comprising a semantic conditional module and a contact conditional module. The semantic conditional module infers the most probable contact maps based on SCM, while the contact conditional module generates controllable grasps under the guidance of tactile guided constraint, TGC. The framework allows for controllable generation by starting from a user-defined SCM. The training process involves using a conditional generation model to infer probable contact maps based on user-specified or algorithmically predicted SCM. The Contact Conditional Module then uses a conditional generation model based on contact maps predicted by the Semantic Conditional Module and constrained by SCM to infer monoparameters. The entire process can be represented as a series of equations, where the output of one module is used as input to the next. The testing process involves combining the contact map predicted by the Semantic Conditional Module with features extracted by PointNet as input to the Contact Conditional Module, and estimating monoparameters. The process is repeated in a denoising step, where the output of one step is used as input to the next. The final output is a controllable grasp that is generated under the guidance of TGC and SCM. The proposed method has the potential to address the challenges of fine-grained interaction and controllable grasp generation. The use of SCM and TGC allows for more precise prediction and control of grasping through user-specified contacts. The Contact Conditional Module and Semantic Conditional Module in the ClickDiff model employ a tactile guided constraint (TGC) loss function, which ensures accurate alignment of fingers with designated ground truth contact areas. The TGC loss, denoted as L_TGC, measures the distance between the centroid of each finger's predefined set of points and the contact point on the object. The reconstruction loss, L_R, is used to train the Semantic Conditional Module and Contact Conditional Module, with the goal of minimizing the difference between predicted and ground truth contact maps and monoparameters. Additionally, a contact map-based loss, L_C, is designed for the Semantic Conditional Module training, focusing on hand-object point pairs systematically selected based on the contact map. The efficacy of L_C is attributed to its emphasis on these point pairs. The training loss for the Semantic Conditional Module is a weighted sum of L_R and L_C, while the training loss for the Contact Conditional Module is a weighted sum of L_R, L_V, and L_TGC. The ClickDiff model is trained on the Grab and Arctic datasets, with object features extracted using PointNet and optimized using the Atom Optimizer. The model is evaluated using 4 metrics: mean per joint position error, MPJPE, mean relative root position error, MRRPE, contact deviation, CDEV, and success rate. These metrics assess the accuracy of controllable grasp generation, including hand posture modeling, contact precision, and success rate. Qualitative comparison results on the Grab dataset demonstrate the effectiveness of the proposed approach, producing more plausible and accurate grasps for unseen objects compared to baseline methods. The ClickDiff model achieves state-of-the-art performance on the Grab and Arctic datasets, with significant improvements in MPJPE, MRRPE, CDEV, and success rate. The results highlight the importance of incorporating tactile guidance and semantic contact maps in controllable grasp generation. The proposed method, ClickDiff, introduces a novel approach to controllable grasp generation using diffusion models. The key innovation is the Semantic Contact Map, SCM, which enables users to define contact conditions by simply clicking on the object. This map is used in conjunction with a dual generation framework and a tactile guided constraint to generate grasps that satisfy the desired contact conditions. The effectiveness of ClickDiff is demonstrated through extensive experiments on the Grab and Arctic datasets. The results show that ClickDiff outperforms state-of-the-art methods in terms of MPJPE, CDEV, and success rate. Specifically, the implementation of SCM leads to a significant reduction in contact deviation and improvement in success rate. The dual generation framework is also shown to be superior to single-stage generation models, particularly when augmented with SCM. Ablation studies are conducted to analyze the impact of different components on the performance of ClickDiff. The results show that the use of SCM leads to a 18.87 mm reduction in CDEV, and the dual generation framework results in a 4.62% increase in success rate and a 7.86 mm decrease in CDEV. The tactile guided constraint is also shown to be effective in ensuring that the fingers align with the designated ground truth contact regions. The proposed method is computationally efficient, with an increase in controllable grasp generation time of only 30% compared to models without contact conditions. Overall, ClickDiff demonstrates superior performance to existing grasp generation methods, both qualitatively and quantitatively, and has the potential to enable more accurate and controllable robotic grasping in real-world applications. The paper introduces ClickDiff, a novel method for generating and controlling grasp contact maps using diffusion models. It leverages the concept of semantic contact maps to predict the interaction between hands and objects, enhancing the understanding of hand-object manipulation in computer vision and robotics. The approach utilizes a deep neural network to estimate the contact map, which is then used to generate and control grasps. The proposed model is trained on a dataset of hand-object interactions and evaluated through various experiments, demonstrating its effectiveness in predicting and controlling grasp contacts. The authors acknowledge the support of the Shenzhen Innovation in Science and Technology Foundation for the Excellent Youth Scholars and the National Natural Science Foundation of China. They also provide an extensive list of references, showcasing the comprehensive research conducted in the field of hand-object interaction, grasp generation, and motion synthesis. The ClickDiff model is designed to estimate the semantic contact map, which represents the interaction between hands and objects in a 3D space. This map is essential for understanding and predicting how humans interact with objects, as it encodes the spatial relationships and contact points between the hand and object. By leveraging diffusion models, ClickDiff can generate and control grasps, making it a valuable tool for robotics, computer vision, and human-computer interaction applications. The paper's approach builds upon previous research in the field, including work on hand-object pose estimation, motion synthesis, and grasp generation. It also highlights the importance of datasets such as ContactDB, HO3D, and Arctic, which provide valuable data for training and evaluating models like ClickDiff. The authors emphasize the need for further research in this area, particularly in addressing the limitations of current methods and exploring new applications for hand-object interaction models.